All right. Hello and welcome everyone. Welcome to today's webinar. Our topic, Advanced Engineering Simulation for Energy Transition. My name is Sarah Alspaugh and I will be your webinar host coming to you live from Cincinnati, Ohio here in the US. And I would like to welcome and introduce our speakers today. You should see their bios in the bio widget on the left-hand side of your screen. You can expand those and read their bios at any time. But I will briefly read from them and then quickly turn things over. With us today, we have John Lusty and Simon Rees. John is the Energy and Utilities Industry Marketing Lead for Siemens Digital Industry Software. He began his career with Dow Chemical and later Nowco Chemical in technical sales as a steam and cooling water chemistry specialist in engineering and chemical plants. In 2000, John moved to the software industry, holding management positions at Allegro Development and Bentley Systems. In 2010, John joined Siemens with roles in enterprise sales, industry solutions, and now global industry marketing. John holds a Bachelor of Science in Earth Science from the University of Guelph. Simon is the Projects Director for Norton Straw Consultants, part of Element Digital Engineering, itself part of Element Materials Technology Group. He did his Bachelor of Engineering in Mechanical Engineering and his PhD in Applied Mathematics at the University of Leeds, and for much of his career has specialized in numerical simulation in the power and energy industry. His work covers the oil and gas, renewables, nuclear and hydrogen industries, leading projects that assure the performance, integrity, and safety of major assets. He is a fellow of the Institution of Mechanical Engineers and as a former chairman of the Upstream Oil and Gas Committee, now sits on the IMECI Process Industries Board. He is also a member of the University of Leeds Center for Industrial Fluid Dynamics Steering Board and a member of the Royal Institution of Naval Architects and a fellow of the Royal Society of Arts. All right, well, welcome to both of you today. We're very excited to have you. John, I know you're going to go ahead and kick things off here, so I will turn things over to you. And attendees, we will be turning our cameras off during the presentation so we don't compete with the bandwidth. All right, welcome, John.
Perfect. Thank you very much, Sarah. And hello, everybody. Good. I don't know if we have any good mornings left, maybe in the Pacific Coast, I guess, of the U.S. Good morning, good afternoon, good evening. I'm glad that you could be with us today to talk about this super interesting subject of advanced engineering simulation and how it applies to energy transition, decarbonization, ESG, that whole theme that we're working on around the world, really, with some pretty impressive targets to meet. Just a couple of notes. First off, very glad to have Dr. Simon Rees with us from Norton Straw online with us, showing my age there. Norton Straw is a very close partner of ours, especially in the field of simulation. And as you heard Sarah say, they're evolving into the next phase of their corporate existence as part of Element, and the best is yet to come. So as you could tell from Simon's qualifications, he has a lot of perspectives that he can bring to bear. And I think you're going to find his presentation when I'm done here to be super interesting. Just one note, when we refer to energy on this presentation at Siemens, we refer to the energy and utilities industry encompasses a number of industries. It includes oil and gas, power generation, all forms, process industry, which are petrochemical, chemical, specialty chemical, materials for mining, for example. So we move a lot of industries under energy. So I typically just say energy, but just as an FYI on that. So as we talk about the world we're living in these days, and it seems to me that I could update this slide every week because something's changing. From the businesses that support our global energy industry, regardless of your business model, whether you're an OEM or whether you're an EPC or whether you're an owner operator in one of the industries that I mentioned, we're all being asked to do more with less. We've got parts of the business community and society asking us to, provide more power, but do it with a greener footprint. Or, we need more supply, but also we don't like intermittent. We want it to be consistent. So that's a challenge. More throughput for lower cost. Again, more for less. That never seems to go away. But now, really, the focus of this webinar is going to be, well, how do we increase productivity? How do we increase production and satisfy the increasing energy demand around the world, and yet do it in a more sustainable footprint? So there's a tremendous amount of innovation underway around the world right now to satisfy these requirements. And as we all know, some parts are going great, some are proving to be a challenge, but at Siemens, we produce a set of tools in digital industry software, and we call that toolbox, the accelerator platform. And a component of that accelerator platform is our simulation tools that work together with all of the other tools to support clients in their innovation efforts. So we often get asked, what does your software do? Well, it depends what you're trying to do. So just like the toolbox in your garage, depends on the project that you're working on in terms of how you would use those tools and which ones you use. But we're primarily focused on deep engineering innovation, and there really isn't a more exciting area right now than energy transition to be working in. Now, the challenge in terms of what comes with that is an explosion of complexity, and this has been gaining ground on us over the years in terms of the volume of data, the sophistication of the tools we're using, and we've got things like hypercomputing, more powerful computers. We've got the cloud, but at the end of the day, it's created enormous complexity, and this can be a challenge for some organizations, or it can be an opportunity. So when we're looking at what's happening in the industry in terms of the trends, we really see two types of customers out there, two types of companies. Those that are adept at saying, hey, within this complexity, there's an opportunity, and we want to get there first, versus others that maybe feel the need to defend against this complexity and how to hedge the risks. And really, the most exciting innovations are going to come from turning that complexity into a competitive advantage. So it's a bit of a blessing, but it's something to hedge against as well. So the analysts are always an interesting group to keep track of. There's clipped out a table here from a study done by the Aberdeen Group. They're one of my favorite analysts. They always have lots of substantiating data. And I liked what they were saying here in terms of how companies are using using simulation to improve their product designs. A product design in energy, it could be a plant, it could be a project, it could be an asset, it could be a system, but collectively, they're all at the end of the day products. And one of the trends that we're watching very closely at Siemens, because simulation is such a hugely important part of our portfolio, especially in the energy industry, is that more and more businesses are using simulation earlier in the development process. There's more of that what-if testing and analysis being done upfront by 73% of the respondents to the survey, which is pretty remarkable. In doing so, promoting collaboration between your R&D experts, analysts, the design engineers, everybody working on this project saw an improvement by using collaborative simulation. We're looking to combine more physics into the analysis to increase the simulation realism, making sure that, hey, once we produce this thing in real life, it really does perform as the simulation suggested. And then lastly, at 42%, capturing expertise of simulation experts, making them more accessible. And that's got to be incredibly important because of demographics as well, as so many of these people are ready to retire. So if you put all this together, these are the various lenses that we look at through Siemens, and then we come back to the industry and say, okay, what's going on in the industry? We try to distill that down to 4 major trends. We've got, as always, and this hasn't changed even with energy transition, but there's a massive pressure on companies to demonstrate superior financial performance. With the level of transparency in the marketplaces, it's very easy now, or certainly a lot easier than it used to be, for people and shareholders and analysts to be able to industry segment players against each other and determine how to best put investment capital to work, which impacts the capital investments in the industry. The energy industry is very capital intensive. It requires a lot of institutional investment, and being able to attract that investment capital, companies in this space are competing with people that are trying to decide, well, should I invest in Google or should I invest in John Lusty Energy, right? Which is going to be, because money is going to flow to where it is treated best, right? As we all know. At the same time, we've got the digital world accelerating, right? And that's changing everything. It's changing the way we produce software, and it's changing the way our customers execute projects and the way OEMs produce equipment, right? Which in many cases are now computers that behave like assets. So that gets a vote in the trends that we're looking at. But most importantly right now, and this is what resulted in this webinar, is the being able to execute on energy transition, which is so important on so many levels and requiring an awful lot of innovation. And as I mentioned at the beginning of this talk, that's where we like to play at Siemens, is bringing deep engineering solutions to help those people that are trying to solve problems on the cutting edge. So internally here, just to wrap this up, we look at all these things, what's happening in the market, what's happening in the business, in the industry, and in the world, and we've distilled them down into what we call digital threads. We looked at what are customers trying to do, right? Are they trying to improve their data management? Are they trying to design the next greatest system out there? You know, are they doing simulation in concert with that to make sure they get optimum performance and shorten that release time as much as they can? Or are they literally trying to get more power out of their plant, less emissions out of their plant, develop mini plants like maybe carbon capture and sequestration to be able to deal with the emissions from those plants? We look at these requirements. We look at our tool set, which is, you know, a massive software portfolio, and we come up with integrated solutions in terms of, they're not products, they're what we call digital threads, and they're tools that work together to emulate the work processes that R&D people and design engineers and operations professionals and process engineers are going to have to work through to execute their jobs. So our world revolves around these digital threads, and that's why today we're here talking about advanced engineering simulation. You will see webinars coming in the coming months on operational excellence, integrated design and configuration. There's a whole bunch out there now on digital lifecycle excellence that were extremely well received. So I would encourage you to keep an eye out for those. Okay, so as we start to now transition over to Simon, I just want to leave you with, you know, when I look at all the software that we're working with and what people are doing with it, you know, I don't see a tool set with greater potential than the world of simulation to be able to try to understand what is difficult to understand and to try to determine using capabilities like design space exploration in terms of, okay, where do I need to go even if I don't know how to get there, right? Let the software and let the computers figure that part out. I just can't see an element of our solution portfolio and all the things we monitor in the energy industry that have more potential than advanced engineering simulation. And I just love this quote from David Attenborough, where, you know, the British zoologist who, and I think I've been listening to him for 40 years now. We are, after all, the greatest problem solvers to ever have existed on Earth. So, you know what? Energy transition is a challenge, and we got one more to do, and we're not done yet. So work to be done. We're going to run a short video here just to break things up a little bit, and then I'm going to pass over to Simon. So let's wait for this video to start up here.
Seamless high-definition simulation provides reliable and realistic results for today's energy and process engineers. So, maximize innovation and harness the power of multi-physics simulation to master complexity and improve predictability for sustainable operations. Empower engineering teams to light the way using Siemens Advanced Engineering Simulation. Remove human bias that can lead to preconceived conclusions and instead create alternatives that no one has thought of before. Connect engineering teams using the cloud to promote collaboration and innovation while improving change management and data reuse. Use design exploration to understand the complex non-linear relationships between process variables and behavior, to think out of the box to achieve operational excellence while improving sustainability. Connect distributed teams with cloud-enabled engineering simulation and test solutions to focus your best minds, using a systems engineering approach to improve teamwork across all disciplines. And empower engineering teams to light the way using Siemens Advanced Engineering Simulation. Siemens, where today meets tomorrow.
Perfect. Okay, so Simon, we get to turn it over to you. So everybody, I think you're in for a treat. As you heard from Simon's bio, he's got a deep background in many areas that are relative to the space, and he also coaches rugby, which in my mind makes him a perfectly balanced professional. So Simon, let's turn it over to you.
Thank you, John. Yeah, that was missing my bio, wasn't it? Level 2 rugby coach. Right, well, thank you very much. Thanks, John. Thank you, Sarah. Thank you, Siemens, for the opportunity to present this webinar. Very interesting, the points about complexity and uncertainty that you mentioned earlier, John. I think it's absolutely a feature of the energy transition, and those are the features that are making it so amenable to simulation as part of the solution. So it's a huge subject. I'll try and do it justice. I'm going to try and focus on some of the more interesting bits and pieces. Plan is to go through exactly what it is and what it means. I'm sure a lot of people are very familiar with the energy transition and the background too. I'll just cover some of that stuff. I'll cover some of the opportunities of simulation, how simulation can be deployed to support the energy transition. And then I'm going to illustrate with some examples. I've got some one-sliders, and then I've got a rather more detailed example at the end on liquid hydrogen as an aircraft fuel. Simulation has been used in a number of different ways to support that program. Before I do that, our marketing people, I'm afraid, to let me off the hook if I present this bit here, explain a bit about who we are and where we came from. We were founded as an independent engineering analysis and simulation business about 10 years ago, mainly in the energy sector, although we diversified fairly rapidly into other areas such as aerospace, chemical process, food, things like that. Late last year, we joined Element Materials Technology as the core of the new Element Digital Engineering business, and we will be changing name at some time later in the year into Element Digital Engineering. We'll be augmenting their global test, inspection, certification businesses with simulation and digital engineering and data analysis, provide a single combined physical and numerical analysis capability worldwide, with the Element having offices, I think 200 odd offices all over the world. So plenty of locations and plenty of opportunities to support people elsewhere. But that's enough about us. That's not why you're here. I'm going to introduce the background to the energy transition, as discussed, and it's largely related to the Paris Agreement, which is pretty well known, which agreed to limit human-induced global warming to 1.5 degrees centigrade. That means zero carbon generations, net zero carbon generation by 2050, and a reduction to 45% of current levels, probably 2018 levels, by 2030. The graph there shows how it would work. The red line shows what would have happened if we didn't do anything. The orange line, where we are now, and the blue line is where we need to go in order to hit those targets. And you see the upper blue line actually ultimately goes negative, because the hope is that we will actually get to a point where we're taking carbon out of the atmosphere with carbon sequestration. You can see the contributions from each one of the major industry sectors: transport, power and heat, and industry being the largest. Transport, mainly automotive, with marine and aerospace also contributing. Power and heat, domestic heat, and as well as power generation, industrial, and for the grid. And industry, industrial processes, anything using fired heat, or even chemical processes that liberate carbon dioxide, such as cement manufacture, fall into that category. Buildings, largely commercial buildings, large buildings such as that, and other is mostly agriculture. Not just the famous cow methane issue, but also the simple process of ploughing actually liberates quite a bit of CO2 from the soil. So agriculture does contribute in quite a way. Oh, I've accidentally skipped one. Beg your pardon. It's doing that. Why is it doing that? Stop doing that. Right. That graph came from the International Energy Agency, and they also predicted that there should be 6 major contributors to carbon reduction. The big two there are renewable energy and end-use electrification. And both of those are obviously ongoing fairly rapidly, and we will talk about those in a bit more detail going forward, because there are some significant challenges caused to the electrical grid by doing things like that. The electrification thing is not just cars, but also industrial processes, domestic heat. In many parts of the world, domestic heat is provided by gas boilers and other similar activities like that. Purely transport. It's also domestic and industrial uses. Energy conservation is already having an effect, and I'll touch on some numbers on that later on. The role of hydrogen is very interesting. Hydrogen itself is not necessarily a green fuel source. It depends on how it's generated. It's probably best seen as a transport vector and a storage medium rather than a fuel source. The number the IEA uses there of 10% is also up for a lot of debate. Some people think that hydrogen could be an awful lot more important than that. That's a working number in there. And down at the bottom, we've got carbon capture and bioenergy with carbon capture, or BECCS, as it's often known. Conventional carbon capture is taking industrial processes or power generation, sequestrating the carbon dioxide and pumping it offshore into disused gas reservoirs, usually, or even onshore disused gas reservoirs or salt caverns. Bioenergy with carbon capture offers the prospect of negative carbon, because it's taking bioenergy, which is in itself almost net zero, but then taking the carbon off that's generated, the carbon dioxide that's generated through combustion of the bioenergy, and storing that in an offshore storage environment. So that's a negative contribution, which is really quite something. And a typical industrial society, and it does vary from society to society, but say a typical industrial society, very roughly 20% of energy is carried by the electricity grid, roughly 40% in natural gas networks in those countries that have them, and another 40% in transport fuel. That's that 20-40-40 split, which is fairly typical. If we're going to use electricity instead of carbon fuel for vehicles and for some industrial processes, then the grid capacity has to increase considerably. Also, the electricity being used to generate that grid has to be almost entirely renewable, 90% of the net zero model because of the carbon sequestration aspects there. Also, the grid installation rate has to increase. If we're going to target 2050 with 3 times greater electricity generation than there is now, of which 90% is going to be renewables, then the replacement rate or the expansion rate of the electricity grid has to be 4 times greater than it is now. This is a major shortcoming in the energy transition at the moment. There's not enough effort being put into electrical grid expansion. In the UK, for example, the rate of grid expansion is about 250 gigawatts per year. It has to expand to over 900 gigawatts per year if it's going to meet that 2050 target. There's quite a lot of work to be done there. This is a fundamental change in the nature of the future electricity grid. We're going from a traditional model where you have a relatively small number of large electricity power generating sources. So nuclear power stations, large coal power stations, even large gas power stations, which are usually fairly widely distributed across a country or a region. And the electricity is transported on a core grid, fairly high voltage, usually 400 kilovolts, and then gradually breaks down into smaller and smaller branches. It's a tree model. It's like a tree. You have a large core and then it branches down into smaller branches. This is going to change because the energy sources are going to become decentralized. We have things such as rooftop solar panels putting electricity back into the grid now. We have domestic biomass generation, domestic wind generation, even domestic heat pumps. It's quite possible for a house to generate more electricity than it uses, and so that needs to go back into the grid. This gives a massive problem to grid stability. Grid stability is usually about the balance between the supply and demand, as seen as changes, or imbalances are seen as changes in the frequency, the electrical frequency of the grid, which is usually roughly 60 hertz. Those changes, if it goes outside a certain bound, roughly 5 hertz each way, are sufficient to knock out equipment. And we've already seen failures in some parts of the country. In the UK, about 2 years ago, there was a problem with a wind farm which went off line very suddenly, destabilized the grid, and led to a temporary blackout. So these problems do happen. One of the solutions to that is going to smart metering. So a domestic electricity meter will be connected to the internet via the grid, but also all the different sources and consumers of electricity in your house, from the fridge to the toaster to even an electric car that is perhaps overnight putting electricity back into the grid, will be connected to that smart meter and will be talking to it all the time. Even that is probably not enough to capture the potential instability of a distributed grid. Modeling is going to have to come into play. There are going to have to be digital twins of the grid running all the time to try and pick up these variations and try and keep the frequency variation within acceptable margins. Some of this is happening already. The EU has mandated 80% smart meters, or did mandate 80% smart meters by 2020. I don't think it quite made it, but it did mandate 80% smart meters by the end of 2020. So some of these changes are happening. The change of electricity generation is also changing. So if you look here at the UK sources for the last 8 years up to 2020, coal in 2012 was still a very significant contributor. But you can see the way that coal has dwindled to almost nothing. And if it hadn't been for events in Ukraine, it would have gone to nothing by now. The last 2 coal power plants got a bit of a reprieve on the back of the Ukraine crisis, but coal would have gone completely. What's curious about this one, though, is you see gas there on the right. That increases to balance for coal, but then it starts to drop. In 2020, it actually reduced. And that's because of the very rapid increase in wind and solar. And there's an awful lot more going in. There's something like 65 gigawatts of wind generation going in the next few years. So that's going to get even greater. So you're seeing this shift to the right, to the left, well, from the left, of wind and solar, and pushing the carbon-based stuff off to the right. One thing I didn't mention there, actually, I should have pointed out, was that the total consumption isn't shown there. It's just shown the percentage. Total consumption dropped by 16% over the same period. And that was largely down to energy conservation measures. Mentioned in the IEA data that one of the key drivers is energy conservation. That's already starting to come through with total consumption dropping across the world, or certainly in developed economies across the world. It's very obvious. This is grid generation, though, and as we move to electrical cars, it's going to go the other way. Grid generation requirement is going to increase because we'll be taking energy out of the energy that's used by hydrocarbons to power vehicles. It's going to switch to electricity. It's going to come from these sources in future. There's three different ways in which we can use simulation in addition to the digital twin approach for actually modeling the grid itself. Firstly, there's the systems model. This is a system of systems, a classic system of systems. It's lots of different systems connected together into a system of systems. And by building detailed system models, we can do things like techno-economic studies. We can look at multi-criteria decision analyses. We can look at different ways in which the grid itself can be using tools. AMOSIM comes to mind. Various other similar tools like that. We can model things. We can use much more detailed or even reduced order models to model the design itself. So we do a very detailed model for design stuff, break it down to reduced order model to do design optimization and space exploration work. Sometimes we can now put these together into federated simulations and start to actually build detailed models of the wider system itself. Federated simulation allows you to put in these detailed models or take them out and replace them with reduced order models and then run them a bit faster and look at different options and different ways of doing things. Ultimately, those design models can be reused as a digital twin for operational models. In this case, we would take something, cut it down, and then deploy it in real time, operating in real time to take condition monitoring data and interpret it using sensor fusion with condition monitoring data. And from that, you can do scenario planning, control optimization, and improve the whole thing. So I think there's three main threads to the use of simulation within the energy transition. There's still some work to do here because a lot of the models that we have used historically, and I imagine much of this audience is familiar with computer modeling of engineering systems, has been at the design stage. And some of that expertise has not always gone across to the operational side of things. And here's an example from the Dutch government, who announced the ending of natural gas extraction in 2018. In fact, for other reasons, they didn't quite get there, but they announced the end of it. And they have a large number of community heating projects, so shared heating systems. And they had to identify alternative fuel sources for these. A lot of work was done with large-scale system models of the heating system and the power sources and things, but they didn't actually manage to get much benefit from that. So a study was set up to work out why the modeling of these systems had gone wrong. And they concluded that although the modeling approaches would add benefit, the problem was that the users on the operating side and the policymakers didn't really have the expertise to do it. And there's a quote there saying practitioners need new expertise to effectively use energy models. So it's not just about the quality and the capability of the models we develop, it's also understanding that the users may not be familiar with some of the techniques that we're familiar with, and there needs to be a process of training and education on that side to get the most out of modeling and simulation. I'm not going to go into some of the more detailed case studies that I mentioned before. And I'm going to start here with a study in battery storage. An awful lot of work needed in storage. People talk a lot about energy transition. We think a lot about how it's generated and how it's used. But because so many of the renewable sources are intermittent, we also need to think about storage. The sun doesn't always shine, the wind doesn't always blow, the tide doesn't always flow, and the sea isn't always rough. And these things are all important for generating electricity. And when that happens, then we need to have a backup. There's quite a lot of techniques being developed, including pumped hydro, which is already widely in use in both the Americas and in Europe, although I think there are more plants being developed. Compressed gas is coming online, both nitrogen and also just ordinary air as a source. Electrolysis to hydrogen, as I mentioned before, hydrogen is perhaps best seen as a storage medium rather than an energy source. If you have too much electricity, you can generate electricity by electrolysis. And there's a company called ITM Power, for example, that's developing relatively small-scale electrolysis devices that can be connected directly to individual offshore wind turbines, and from that generate hydrogen that can be pumped ashore in the gas network. And most obviously, of course, batteries. And in this situation, a potential investor wanted to develop manufacturing facilities for liquid flow batteries. Liquid flow batteries are an interesting technology. They're really for larger scale energy storage rather than for vehicles or domestic applications, because they use a liquid catholyte and analyte, which are pumped together through an ion exchange membrane and generate electricity that way. They can be scaled almost infinitely because it depends on the size of your tank for the analyte and the catholyte. They have great safety benefits because they usually are differences of the same chemical. So there's no chemical risk from them coming into contact. And they also have better use capability, and the recharge rate of decay of charge holding is much lower than the likes of lithium ion. And if it does decay, then you can top up the analyte or catholyte rather than just chucking it away and starting again. So it's great many benefits. This particular investor was faced with a situation that there were a number of different competing technologies. Some were licensed, some were not licensed. They needed different potential investment in manufacturing facilities. They had different market positions because different scales and different capacities, and overall different risk reward. So a techno-economic study was needed to identify the best way forward for this particular customer, the best engineering solution, best technology to invest in. And to do that, we did it in two strands. We modeled the performance of each individual technology to work out where each one sat within the market, what the benefits were of the different systems, and also classic net present value, commercial modeling, financial modeling of the plants themselves to work out where the different returns came in. And this was coupled to then investment study into the investment necessary for the manufacturing systems. It worked very well. We used Amazon for the system model of the generation process and concluded that actually there was a very strong business case for investing in this particular technology. I mentioned reduced order models earlier on. This isn't one we did, but it's a very interesting example of how reduced order models can accelerate the process. Optimizing a wind farm layout is a notoriously difficult analysis problem. The wind blows from different directions at different strengths with different degrees of turbulence in the atmosphere, and there are different wake patterns that form behind the individual turbines, as you can see there, and they impact on other turbines arrayed behind them. So a lot of work goes into getting the optimum layout of an offshore wind farm in particular for different wind conditions. And the best example is seen in the Horns Reef project of Denmark, which has a gloriously curved layout of different turbines designed to capture the best wind. But building these models is incredibly expensive and time consuming. It's not an easy thing to do and not an easy thing to get right. So Stanley and Ning looked at a reduced order model. And a reduced order model is different to maybe what you might regard as a first order physical model. A reduced order model is starting from the more complicated model and then cutting it back down, applying simplified relationships to things that you can predict using the larger model, response surfaces, things like that, and come up with something there's a cut down complex model as opposed to a built up simple model. And that allows you to pick up more of the second order effects, third order effects that you might miss with a simpler technology. But it does require that you have a good model to start with. They reckoned that they could reduce the complex model to 5 variables and get performance within 0.5% of the more detailed model. And that allowed them to start modeling all sorts of different wind combinations in a lot more detail. Now, one thing their paper doesn't talk about was how that could then be used as part of an operational digital twin, but I'm absolutely certain it could. Transport is another one of the key areas where we need to make savings in carbon. And electrification is the obvious solution for rail. There is electrical technology out there that can be deployed, but it's not cheap. There's an awful lot of unelectrified rail out there, and installing it is both time-consuming and expensive. In the meantime, there are areas that are electrified and areas that are not, and some rail routes run across them, particularly in congested passenger route areas. Battery power could be used to bridge those gaps as a potential solution, but the battery itself is potentially quite large and heavy. It has to be charged over a period of time, and of course the size of it means that it consumes some of the passenger carrying space of the train. So you want to optimize your battery selection to make sure that it minimizes the space consumption and is still able to be charged within the right time. To do that, we used models. This is another Anderson model, actually, where we modeled the route of a train of a particular application. And we had to work out what the gradients were, the friction against the traffic, crossing points, planned and potentially unplanned stop locations that might occur, accelerations as it pulls away from stations, and also take into account the charge. It has to charge while it's on the electrical juice, as they say, and that must occur sufficiently within the time it's on the electrical part of the line to carry it through the non-electrified part of it. And in this particular case, the end point of the line was also non-electrified, so there had to be an electrical installation facility there, an electrical charging facility there, and that had to be able to provide enough power to power the return journey. A fairly detailed system model was required, but it came up with that's the optimum size of battery, which I believe is currently in service. More detailed analysis is perhaps a little bit more amenable and more obvious to many of the people on this call. This is a Star CCM Plus model of a large-scale hydrogen fuel cell. This was for industrial use, so it was a big one. And they wanted to reduce flow non-conformity in order to optimize the performance and also increase the catalyst life within the design. So we had to rapidly assess a whole series of design variants, but also look at different scenarios, particularly startup and shutdown, to make sure that it would perform appropriately. Hydrogen is a useful fuel because it can be potentially substituted into the gas grid, but there are also some risks associated with that. And one of the things we went on to do with this was look at some of the safety issues. It's a very wide flammability range, famously so, starting at 4% up until about 90%, at which point it could potentially explode. It's also got a very uncertain, what's called a detonation to deflagration to detonation transition point, to the point at which the shockwave becomes supersonic and it ceases to be just an explosion and starts to become a detonation with very much higher overpressures and an awful lot of damage. And it's also very diffusive. It'll diffuse through sealing systems that other gases might not because it's a very small molecule. However, it's a very appealing energy transport approach. The UK is moving to 20% hydrogen in its natural gas grid from 2025. And to support that, a lot of work's been done on modelling boilers, both industrial and domestic, gas burners for cooking, all sorts of different applications. And then also the safety studies to go with that. And this was a bit of work on the external containment of a hydrogen fuel cell, the same hydrogen fuel cell shown before. And what we're looking at here is what would happen during the startup phase if there was an explosion within the vessel. So we use CFD to calculate the gas dispersion and see what sort of flammable gas clouds might exist within the vessel of different concentrations. Chemical equilibrium simulations to calculate the overpressure that results from the explosion. Of course, being a pressure vessel, it's a constant volume explosion, not a constant pressure explosion, and that makes a difference. And then FEA to see whether or not the vessel would fail. Beyond that, we could say where it was likely to fail, and the missiles that would be generated could be then analysed to see what sort of penetrative energy they'd have and whether they'd be able to pass through any protective barriers or enclosures around it. It's the kind of thing that's impossible to test. You can only do this by simulation. So it's very important that we use it that way. At the start, I promised a rather more detailed one, and this is liquid hydrogen sloshing within an aircraft fuel tank. It covers work done by the Aerospace Technology Institute in the UK on hydrogen-powered aircraft. The hydrogen itself is stored as a liquid in a tank in the fuselage rather than the wings in a more conventional way. And as the liquid hydrogen heats and boils off, there's a risk that the pressure in the tank will increase to a dangerous level. And the point of this study was to calculate whether the sloshing of the liquid in the tank would accelerate the boil-off of the gas and accelerate the pressurization of the tank due to increased surface area and mixing between the gas and the liquid components. The model had to capture the wall heating effect, wall boiling effect shown at the bottom of the diagram there, and also the interface heat exchange between the gas phase and the liquid phase as it sloshed about. Now, validation was obviously extremely important. This is a very, very novel bit of technology, and so we need to make sure that the modeling we're doing is right. There's not an awful lot of data on liquid gas heat transfer at walls, but there is some data around nitrogen. There's nothing at all on hydrogen at the moment. There is some data around nitrogen, which is because nitrogen is often used as a cutting fluid in subsea cutting. So we had data on liquid nitrogen jet impingement onto a metal plate, and we could predict the transient plate cooling using CFD. So StarCCM Plus model of coupled liquid nitrogen, obviously with all the thermodynamics and phase changes that come with that, and then the subsequent cooling of the plate. We were able to get fairly good model results of that, but at immense computational expense. In order to capture the behavior, we needed very small cells, and that led through the CFL restriction to very short time steps. And you can see there some of the agreements we were getting, which was very good. But we had to come up with a better way of doing it. So we developed an approach of decoupling the fluid flow and transient conjugate heat transfer timescales to speed up the simulation by more than 2 orders of magnitude. We had to do that right, though, because obviously the degree of decoupling affects the accuracy of the model. So we had to do different models of different degrees of decoupling to see which worked best. And you can see from these plots here, 2 different time-stepping approaches and the better accuracy that we got by optimizing that decoupling from about 20 degrees out to about 5 or 6 degrees out, which we thought was rather good, to be honest. So we went with that method as the way forward. We then had to model and validate the interface heat transfer and the direct contact boiling that happened. And again, there's not a lot of data on sloshing of liquid hydrogen, so we had to use a surrogate. There is some data on a high water and steam tank, and these have been used as a test basis as a way of studying natural gas, LNG tanks in large tankers. The sloshing is induced by the rocking of the tank. The water is initially colder than the steam. This is slightly different, but we could work with that. So the sloshing of the tank happened, and the tank pressure was seen to drop as the steam condenses, which was not quite what we were expecting, which was interesting. The StarCCM Plus model of the tank was built quite successfully, and the Rosenau model within StarCCM Plus was used for the interface boiling. We did make one small improvement using the user-defined function capability, and that was we optimized the heat transfer times area parameter there. The default value in the system wasn't quite right for a hydrogen situation or steam situation in this case, so we found a new physics-based closure model and applied that within StarCCM Plus to get a slightly improved boiling model. As you can see, we got quite good agreement with the validation work and the experimental work, very consistent with what's going on, and we managed to explain why the pressure was dropping rather than increasing, and that was simply because the heat transfer was happening the other way. Rather than the gas heating up the liquid and making it boil off, it was the other way around, and in fact we discovered that sloshing was a good thing for a liquefied hydrogen tank in an aircraft. That was good because the alternative was to introduce baffles to stop it from sloshing. Those baffles would have acted as heat paths and actually made things worse. So this was a good result. On the next slide, I'm going to show one of the lovely, pretty pictures of sloshing that you can get from multi-phase CFD animations. It runs fairly briefly, but it does show the trick. And we then went on to run these models for liquefied hydrogen in different air conditions. So your classic gust loads and maneuver loads in aircraft. You can see the sloshing pattern there. So in conclusion, things are happening quite quickly. I think more quickly than a lot of people realize. In the UK, the sale of internal combustion engines will be illegal by 2030. And John said at the start in Canada, it's by 2035. That's not very long at all. You know, it's only 8 years' time in the UK you will not be able to buy a petrol or a diesel car or a truck, which is possibly a bigger challenge. I don't think any of the things we're talking about, the energy transition objectives we've got, are achievable without using a lot of simulation to study all the different options and all the different ways of doing things. So I think simulation has a massive role to play, both in simulating the wider system, the systems of systems, and also the details of the individual technologies we're going to have to use. So thank you very much for your time. I believe there's questions been submitted, and I think Sarah is doing the honors.
Yes, thank you so much, Simon and John. I would like to thank our attendees for joining us. You will receive a follow-up email with a link to view the recording, so you can, of course, watch that again, and definitely do share that with your colleagues as you see fit. If you think of any additional questions after we close, you can email me directly at sarah.osbal@siemens.com. You can also connect with me on LinkedIn and message me there. And I think that John and Simon would be honored to have you connect with them on LinkedIn as well.
Absolutely.
And finally, I would just like to encourage you to visit our website, sw.siemens.com. There you can try our software and learn more today. And this concludes today's webinar, everyone. Thanks so much for joining us, and have a great rest of your day.
Excellent. Thank you.
Thank you.
Thank you for watching. To learn more about this topic, check out the links in the description. And if you enjoyed what you saw, like the video and subscribe to the channel.